Hello. This is a presentation about Clojure's transducers that I recently gave to the Austin Clojure Meetup. I discovered that a bunch of our members were experienced Clojurians, but they weren't yet using transducers, and they didn't really know if there was a reason why they should be using transducers, maybe didn't know exactly what they were or where they would apply. So I wanted to give this talk to the group to help them understand a bit more about transducers and then really to make sense of them and what they're useful for. In a nutshell, the goals of this presentation are really just to introduce transducers, also to show how to use them. I'm going to show the basics of how they're implemented, which I think is really helpful in understanding exactly what they are. I'm going to describe their trade-offs. When is it right to use transducers or other mechanisms like lazy sequences? And then finally, I'm going to try to convince you that you should probably be using transducers today. So, what are transducers? Well, per the transducers reference page on the Clojure website, they are algorithmic transformations that compose. They're independent of the context of their input and output sources. So they're really these building blocks that specify only the essence of the transformation that we want to perform in terms of an individual element. We can use them a lot of different places, which is really cool. We can use them to transform collections, which is a pretty common thing that we do in the Clojure world. But also we can use them on streams or channels or observables or really anything where we want to transform a series of values. It's a pluggable mechanism we can apply to new quote unquote processes that we've created or others have created. They're really quite flexible and they compose directly. So we can really take these pieces of the transformation process and plug them together without concern for exactly what it is that we're transforming, which is really important. Finally, they don't create intermediate aggregates, which basically means there aren't these intermediate products created during the transformation that will need to be garbage collected. We'll talk more about this later. I want to say, both with regard to what we just looked at and Clojure documentation in general, whether that's doc strings or documentation on clojure.org, it has a unique style often. It can be really brilliantly dense. But the one factor with that density is that every word carries important weight, and sometimes when we miss a word in that documentation, it can cause us to lose the thread on what it's trying to say. I really feel that they're often designed for experts or for the experienced, which is a wonderful thing when you are that experienced person visiting those docs just to refresh your memory or extract a small detail. But sometimes it can be a little rough when you're just getting started to try to absorb that content and to realize the importance of every word and why each word is chosen so carefully in that documentation. So I think it's really important to have additional educational resources for people of different levels or trying to achieve different things. There was a great talk at the Conj last year about the practice method of documentation, which talks about 4 different types of documentation that are important. And I think this is one of those examples where sometimes the official docs aren't necessarily the best resource to learn these things from. Or maybe there are increasingly multiple kinds of official docs, but the simple documentation of the functions, for instance, is often very challenging to get the whole picture from, hence this presentation. Of course, this is a Clojure talk, so we have to talk about etymology. Transducer is this word that goes back to 1924 that is about converting energy from one form to another. It comes from these 2 roots, trans and ducere, both of which go back to Proto-Indo-European language, so they're some of the oldest roots that we have, right? So these are very old fundamental and basic concepts in really human language. But in Clojure in particular, I think it can also be helpful to frame this like this word comes from transform plus reducer. This will make a little more sense later. As far as the history and adoption of transducers, they've been in Clojure since 1.7, that's 2015. So they've been around for quite a while, and there are more than 20 functions in the core library that can produce transducers. You may not have noticed there were that many. Sometimes they're kind of hiding in plain sight, but there really are. It's deeply integrated with the core capabilities of Clojure. The idea is really well regarded. It's been adopted into other languages, including JavaScript and Python, where this idea that really stems from the Clojure world was recognized as being very valuable and adopted into these other communities. So the takeaway here is that this is mature. This is not something freshly added to Clojure. It's not something experimental. It's a deeply integrated, well thought out, well regarded tool that is a key part of Clojure. So what problem are we trying to solve here? Our traditional transformations of data that we use every day, like map and reduce, actually complect what they are doing with the underlying sequence types. So these functions tend to return lazy sequences specifically, right? And I think we've all probably run across this where we had a vector, we wanted to map over it, and what came out the other end was a lazy sequence. And maybe what we wanted was a vector, right? But that function changed it because it has an inherent output type. Similarly, what if we map over a set? It's a very reasonable thing to do. Maybe we have a set of keywords and we want to map those to strings, and then what we get out the other side is not a set, but a sequence. Finally, what if we have a rougher by analogy type of mapping where we have a core async channel or some sort of observable process, right? Where we still have values flowing through this thing. We want to transform those in an analogous way to what we're doing when we map over a collection. But those tools don't work there because the input is of a different type. So should each of these scenarios require their own functions? Do we need a map V that outputs vectors? Do we need a map S or map set that outputs sets? Do we need this explosion of all these different things? Or is there a more generic way to tackle this? Second, performance is a big question. The lazy sequences that are produced by all these functions we use every day, they're amazing. They actually have some really interesting and beautiful qualities, but they also have a very real performance cost. Should we have to pay that cost if what we're looking for isn't a lazy sequence? If we just have a small vector of a few elements, we want to transform it into a small vector of a few elements. Do we need to construct this lazy sequence under the hood? And then finally, when we map over things multiple times, or we map, filter, and take, right? We've composed these transformations on sequences. We're compounding the overhead, right? There's a difference between mapping to composed functions and just running map twice. And we pay for that in performance. But fixing that, quote unquote fixing, squeezing out all of that performance can really cause the readability of that code to suffer. So we're sort of caught on the horns of a dilemma where we have to choose. Do we want to be fast or do we want to be readable? And that's unfortunate, and transducers can help there. It's worth saying that map V, for example, which people will use to force eagerness of a mapping, it helps a little bit with this, but it is clearly not a holistic solution to the whole question of sequences being produced by traditional transformations in Clojure. So let's talk a little bit about the lazy sequences that are produced by these traditional transformations like map. I find that a lot of Clojurians don't actually realize the complexity of what's happening under the hood. And that's actually pretty amazing that we can successfully use these tools like map and filter and take without really understanding that there is something very complicated happening under the hood. But sometimes you do need to know, and especially when you start thinking about performance, you do need to know. And what these things are really doing when we have a chained pipeline of these transformations is that each function is producing a sequence that is buffering up elements in batches of 32. So if we have, let's say we have some values in our input, we're mapping over those and incrementing them, and then we have a filter after that. Effectively, what's going to happen is that filter is asking the map for for a chunk of 32 elements. The map is pulling in values from its input, And that filter blocks until map has 32 things to give it, right? Then it gives those things to filter, it filters to some number, and then control goes back into map. So there's actually this really interesting and complicated dance happening. And the reason that that is batched is for performance. It's more efficient than jumping around with every element. But we often think about it as if each element is going from the input to the map to the filter, right? And it's actually not quite that simple. And we don't worry about these things too much a lot of the time, but when you're just getting started with Clojure, often you realize something funny is happening in here. The first time you try to put a print line in a map and it doesn't print all of the elements and you're very confused. Of course, side effects in map are not generally a good idea. But as a beginner, you don't always know that. And another scenario where this comes up a lot is when we have a with open statement. Let's say we're reading a CSV file, we're reading in lines, transforming those lines inside of this lexically scoped with open, and suddenly we get an exception when we try to ultimately use those values we read from the CSV file. And it can be very confusing and jarring when that first happens. And the reason that that's happening is because this lazy sequence is being returned that has not been fully realized, effectively meaning the file hasn't been fully read. Then we leave that lexical scope, the file gets closed, and suddenly the sequence can't read those elements from the file anymore, those lines from the file. And that's a surprising behavior if you don't understand how the laziness under the hood works here. This may be a bit contentious, but I actually like to contend that lazy sequences are a concurrency mechanism. If you think about this, it's not a mechanism for parallelism. It's important to understand the difference, right? Parallelism is literally two things happening at the same time, but concurrency is the illusion of multiple things happening at the same time through transfers of control. And in what I just described in that map filter pipeline, you'll recall that the flow of control is moving from the map that's reading and mapping over to the filter that is taking some of those values, then it gets enough values and control transfers back to the map. And that's actually a really powerful concurrency mechanism because it lets us process lazily files that are larger than we could fit into memory. And that is awesome, right? We don't just read the whole file into memory and then go to work mapping each element and then go to work filtering each element. We have this really awesome flow control thing happening that achieves something really powerful in terms of our memory usage. I think they have a lot in common actually with Unix pipelines. So there's this complex blocking flow control, right? So if we look at this example, this is similar to what I was describing. We're reading in this file, we're getting a sequence of the lines, filtering those lines, and then taking three. And if this were just an eager process, let's say there are a million lines in this file, we might read that whole thing into memory and run out of memory before we even got down here to this take, right? But that's actually not how it works in line with how I just described. Actually, this take, we're only going to read as many elements as it takes to kind of get a full batch, i.e. 32, over to this take. And then it's going to try to take three. And once we've taken three, we don't ever read the rest of that file. There's no need to do so. It's sort of quote unquote smart enough to not read much more than it needs. It would be a bit of an oversimplification to say it reads no more than it needs, but it doesn't need much more than it needs because it's operating in these chunks of 32. So similar to this Unix pipeline, right, where we're reading in this file, and yes, I know this is unnecessary use of cat, but I think it just makes this example clearer with the parallels between these two. We're reading this file, we're grepping it, and then we're just taking the first three lines. And there actually is a similar kind of batching happening. And the batching that happens in Unix pipelines is actually at the byte level. So each pipe will accumulate a certain number of bytes before it basically stops the flow and waits for those bytes to be read out, right? So we have a similar notion of laziness. It's not element oriented, it's byte oriented. But in the same way, we can process an extremely large file. We're not going to blow out our memory here, right? We're going to read a bit, we're going to grep that, we're going to send to head, and if head gets to a point where it has 3 lines, it's going to close this pipeline, which is going to tell grep it should shut down. It's going to close this pipeline. It's going to fall all the way back, and we're going to be done. So very similar story to what happens up here. One difference is that the pipe version is truly parallel, right? These are running as separate processes. And like we said, they're buffering on a byte basis. So they're not waiting for something to ask for values before they produce them. They're all just writing to their little pipes, which are kind of like tiny temporary files in a sense, versus the Clojure version, which actually the first thing that runs is really after we've set this up. The first thing that effectively happens is that the take says, I want some input, and it asks filter for it, right? And filter says, hey, I want some input. It asks line seek for it. So it's slightly different, but in terms of the outcome, it's actually quite similar. And if you think about what it would take to write something like this directly in C, let's say, it would actually be quite challenging, right? The flow control is not trivial to write, but these few lines of Clojure are trivial to write to achieve that same power, and that's pretty impressive, actually. Now let's talk about transducers. I think it's best to start with the usage of basic transducers, not yet to worry about exactly how they work, but just to get started with them. And we'll see quickly how they differ from those lazy sequences. And then later we'll work back into how would we actually build them and how do they work. Here's some simple data I'm going to use for a couple examples. Notice we just have this vector of maps representing programming languages. They each have an ID and a broad family that they come from and the year they were created. And then this is the current year. You'll see these things used later, including this require, which is why it's in here. So let's take a look at a familiar transformation pipeline, the way that we would traditionally write it, right? So we're going to take those languages that we just discussed. We're going to filter those down to the ones where the family of the language is the keyword Lisp. We're going to map over them doing a few different operations. We're going to get the ID. We're going to convert that to a string. We're going to capitalize that string. And then we're going to take one element from this sequence. What we get out is the sequence closure, right? These pipelines can be mechanically transformed into transducers. So for the moment, I don't want you to worry too much about how this all works. We'll circle back to this in a second. But just look at how much is syntactically the same between these two. The only thing that has changed is that we've wrapped these 3 forms in a call to comp. And then we've wrapped that in a call to into with an output sequence type. You'll notice here in our output that this is a vector rather than a sequence, right? That's specifically because we said here that we wanted a vector. This is how transducers work. We always say what we want, right? So this is under our control already, which is pretty cool. And now I'll explain a bit more about how this works, right? I already mentioned the code stayed largely the same. We chose the resulting sequence type. But one interesting thing to note here is that because we've taken all these transformations and wrapped them in this comp call, this value that we get back, whatever it is, right, we may not even know yet, but we can kind of tell that this encapsulates these 3 operations. So we have a single value that will filter, map, and then take. And that's really interesting because that means that the essence of the transformation we want to perform has been wrapped up into a single value. And that thing is a function, we know because we've composed it. Specifically, that thing is a transducer, which is a type of function, but we'll get into that more later. The cool thing about this is we could def this, right? We could we could pass it as an argument to another function. We've escaped this idea of, hey, we're just going to map a particular function over a collection. And we've said, bundle that up, store it somewhere. Maybe we want to use that again, right? That capability is not something we could really do in the same way with a traditional transformation pipeline. In terms of the mechanical transformation that we've done here, it does look like these functions are missing arguments, right? Typically, we'd expect to see a sequence here or a collection at least as the second argument to something like filter or map or take, and that is entirely missing here. We're not threading into this slot anymore. So something new is happening, and actually, we're not missing arguments. As it turns out, these functions all have one-arity forms that return transducers. It's easy to miss that if you've been using these functions for a long time and always think of them as taking two arguments. There's another way to call them that returns the transformation rather than kind of running that transformation. More on this later. Finally, the order of the application of these functions appears to be backwards, right? If you think about a traditional composition like we have here, right, the first thing that happens is ID, then name, then capitalize. In fact, in mathematics, comp FG is sometimes referred to as F after G, right? But we're using comp on these transformations that clearly we want to run from left to right, or in this case, top to bottom, not in this style. So this looks backwards. It's really just kind of a quirk of how they compose. They compose in a different order than they actually get run, which is perhaps a bit like middleware and ring applications if you're used to that. But this is one of the reasons that I recommend just kind of focusing on the mechanical transformation first. Like we just changed what we had to wrap these in comp and then to call into. And that's most of what we need to worry about here. So again, I'm a bit ahead of myself, but we talked about these one-arity forms of map, filter, and take, and how the composition works. And then finally, the last thing that I did not mention is that the into function has a three-arity form that applies a transducer to each element in the sequence. You may be familiar with into just to kind of convert one collection type into another, right? We can say into set vector to kind of pour the elements of that vector into a set. But it turns out that there's a middle argument, a second argument that we can pass that is a transformation to do as we are transferring, quote unquote, those elements into the output sequence. So what did we gain by changing this, right? We've done this mechanical transformation to make this transducer version, but what's really different and, does it matter? Well, one thing we've gained is that we have these composable transformations that we mentioned are values that really capture the essence of the transformation. We also gained control over the result type. We showed that we were explicitly saying we want a vector out of this. We could have said we wanted a list. We could have said we wanted a set, etc. Right? So we have some increased power there. We also have a lot of improved performance, actually. So by doing it this way, there are no intermediate sequences generated. Remember, I talked a little bit about how the flow of control worked between things like map and filter, and it was bouncing back and forth. Along the way, it was also generating these temporary sequences that would need to be garbage collected after the fact. And those that garbage obviously leads to increased memory usage, but the garbage collection also leads to pauses in our program, delays in performance. So transducers efficiently use transients under the hood. If you know what that means that there is mutation happening, but it's hidden away in a way that's entirely safe from us, that lets us do this at the maximum possible speed without worrying about safety. So really best of both worlds between immutability and the performance of mutability. Our compound transformations get merged into one pass. What this means is that if we're mapping twice over the same sequence, while we might worry about the performance of that in kind of a lazy sequence land, where we know that we're generating intermediate sequences between those two mappings and all the downsides that go with that, in transducers, those actually get fused into a single operation that is just as efficient as if we had manually composed those mapped functions ourselves. This is really cool. And then, none of this lazy seek overhead at all. We don't have to construct any new things. We don't have to worry about any of that. It's beautiful. We also have increased applicability, right? We said earlier that this transformation that we now have, that is the composition of those different operations, the map, filter, and take, is now one thing, and we can use that to transform the values flowing over a core async channel, or really anything else. We'll talk a little bit about that later and how we can apply these things to new processes, as they're called, transducible processes. Another thing that we still have is a la carte laziness. So what I mean by that is that transducers by default are eager. They're going to run these transformations for all of the elements in the input sequence. They're going to produce a realized output sequence, like let's say a vector. We're not waiting around to read more values from our input. But actually, we can, if we want to, we can still get some laziness using the sequence function to apply our transducer. I won't really cover that much in this presentation, but just know that that is an option. So we have basically a choice of how we want to do it. There's some small differences between doing that with a chain of traditional transformations versus with a transducer via sequence, but it's really cool that we still do have the capacity to have laziness where we want it. So I've talked about the composition of transducers, but when I describe those as composable algorithmic transformations, or when the official docs do, you may wonder, like, well, aren't regular functions composable algorithmic transformations, excuse me. And they sort of are, right? But if you look at the shape of that process, in this example, we're going to take some input, we're going to filter it, and then give it a name, right? So what is being named here? Well, what is being named here is actually not the transformation, it is the transformed sequence, right? And that's very different from giving a name to the transformation itself. If we wanted to transform something else, that's not what we have here. So there's definitely a different form of composition here. And if we look at transducers, instead of having a sequence that comes out of this, right, we are taking the transformations themselves and then composing the transformations, right? So once we have this, we can apply this transformation to different things, to different types of things even, right? So it is really the essence of how we want to transform. It is not a chain of further processed sequences. I talked a little bit earlier about fusing the transformations, right, and the efficiency involved there. If we look at this example of a traditional transformation pipeline where we're taking those languages, filtering to certain ones, mapping over them, and then taking a certain number, if you've been doing Clojure for a while, you'll probably think, well, this would be a lot more efficient if we did the take earlier, right? Let's pare this set down to just the one that we want, and then let's map it to transform it instead of doing a bunch of unnecessary work for multiple values, right? And because of chunking, we're actually not going to do this process for every element of the sequence, but we're probably going to do it for a full chunk of 32 values, only to take one and throw away 31 of them. So it is a bit wasteful. Also, if you look at something like this, where we have a chain of mapped operations, this is not very efficient to do it this way, and it would certainly be more efficient if we comped these things. But maybe we like how this reads, or maybe this doesn't all happen in one place in a single file, but we progressively pare down this data as we pass it through a series of functions. These things happen, and sometimes for good reasons, but they're certainly not as efficient as they could be. And the cool thing, though, is with transducers, the fusing of those would happen automatically. We can write the code this way with separate map operations, and we will get all the efficiency as if we had written map, comp, and then these three functions. So that's pretty cool. as I mentioned, with this map before take, the chunking does help, but like here's really what it would look like if we kind of did everything we could with the traditional kind of style of sequence operations to make this hyper efficient, right? We would write it in a very different style where potentially we used keep to just find the values that we wanted and just transform the values that we wanted. But again, this loses something of the essence of what we're trying to do here, right? We've kind of optimized this at the expense of readability. And also, it really requires having the ability to rewrite all of these pieces. So kind of having them all visible and not having them in separate functions that maybe we liked how that read, to break them up that way. We really have to blast that and say, okay, now what we care about is optimization over all else. And so now we're going to fuse these logical things into this one performance oriented call to keep. So it's not always great to do that. But with transducers, they are really on a per element basis pulling exactly what they need. They're not processing extra elements, they're not operating in chunks, and they're not using anything they don't need. If there's a take one at the end of that transduced process or transducer process, it's just going to take one element and it's going to eagerly reach back through that process and say, give me one. And perhaps what happens prior to that is a mapping. So we're going to map one. And perhaps what happens prior to that is reading one line from a file. And we're going to read that one. Essentially, file IO, maybe buffered, so I may be rounding the edges a little bit, but the basic story is that, right? We're just taking what we need, so we can still write it in the most expressive format, and we don't need to have control over the entire transformation pipeline or rewrite our whole program oriented around optimization to get the optimal result, which is great. We've talked a bit about performance, but how big of a difference does it really make? Well, there's a great write up on this on the Clojure Goes Fast blog. I'd recommend you go there and read it yourself. It didn't seem necessary for me to reproduce this. I just want to show the conclusions they came to, right? But if you look at the kind of classic way of doing it, where we're lazily mapping, let's say, we have this 400 microseconds and 480 kilobytes allocated per call, right? And the transducer version is this bottom row, and you can just see this massive difference in memory usage and in call time, right? So punchline is that 6.5 times faster and allocating 16 times less for the same result. If we just use an eager process, and then if we go all the way to transducers, we save even more, right? So this is a huge difference in memory usage, and it's an order of magnitude in time. So there's a very real cost to lazy sequences. They have their advantages around memory usage, but other than that, they are costly. Okay, so now that we've looked at the mechanical transformations, how do we actually use these? In general, what are the different ways that we can use transducers? First off, I want to compare to the reduce function. So one of the common ways we use transducers is sort of the reduce-like way, right? So here's a basic transformation using reduce. We're going to take our languages, we're going to map over them and get when they were created, map again to figure out the delta from the current year to when they were created, and then sum up all those years by reducing with plus, right? And we get 80. If we did the same with transduce, you'll notice we went through largely the same mechanical transformation, right? We took these two map calls, bundled them up with comp, and then instead of calling into, this time we've called transduce, which is like reduce, right? We're giving a transducer, we're giving a reducing function, and then an input sequence. I think it's worth talking about reduce a little bit because reduce is really foundational to a lot of what transducers do. And if you've never thought about it this way, reduce is really a functional Swiss Army knife. It can do a tremendous number of things. Most commonly in Clojure, we see them used kind of a couple different ways. One, I'm calling the homogeneous type, which is where we're kind of reducing from, let's say, an A and an A to another A. Okay, so in this case, from an integer and an integer to another integer, right? Here's another example of the same where we're going from maps, right? So in each iteration, we take two maps and our output is itself a map. And similarly, when we're working with, let's say, strings and we're concatenating them, it's the same kind of thing, right? It's a sequence of strings, we're outputting a string, and here I'm just showing a case where we do use an initial value, also a string. So homogeneous, right? They're all the same types. There's also this sort of asymmetric or aggregative type that we see a lot. In this case, we typically have like an A and a B, and we're producing an A at each step. So what I mean by that is like in this very common kind of example, which is basically the frequencies function. At each step, we have this accumulator, which in this case is a map, and then we have some x value, and we update that accumulator with a count to have the new accumulator. When we do these asymmetric types, we always supply an initial value. And the reason is because, the first value in the input collection is not the right type of the output, right? So we kind of said, okay, there's an accumulator and there's an x. Well, these are all X types, so to speak. So they're not suitable for the initial value here, right? So we need to provide this initial value that will be called as the accumulator the first time. Probably this is all simple recap for you. But reduce can do a lot more, right? So we can implement map with reduce. And very trivially, we reduce, but this time all we're doing in the reduction is to apply f to x and then conj that into the accumulator. As you would imagine for a map function, we apply the function, we stick the value in the output sequence. Okay, we could also implement filter, and obviously that's very simple as well, right? If the predicate called on x is truthy, then we're going to conj the value onto the accumulator. Otherwise, we're going to return the accumulator unchanged. And then here we just ask for the odd values of the sequence and we get them. A reducing function, that thing that is passed as an argument to reduce, which we commonly note with the letters RF, it just takes the form of, like, as the Clojure docs say, a whatever and an input to a whatever. In some cases, that kind of homogeneous type, the types of these things are the same. So it's kind of a whatever and a whatever to a whatever. But this is, maybe more clearly recognizable as the second case. The whatever is, say, the map, the input is, say, a keyword, and then the output is a map again. You may not have realized this, but one particularly notable reducing function is conj, right? We said we need a whatever and an input, and we return it. That is exactly what conj does. The first thing it takes is a collection, the second thing is a value, and it returns a collection modified, right? So the into function in Clojure is basically just calling reduce with conj to add the values in from to. Like, this is exactly analogous to the two argument form of into, right? We now know there's a 3-argument version that can take a transducer. I haven't shown that here, but so this is just the basic version. Now I want to talk a little bit about duality. So you've probably heard of this famous wave-particle duality of light, right? So which is this concept in physics where physicists discovered that light shows both properties of waves and particles at once, right? And there are certain experiments done, like the diffraction grating experiment, that showed one form of light behaving like waves or light behaving like particles, and there were other experiments that kind of showed the opposite. And we kind of learned that it has both of these properties, but sometimes it's easier to understand it when thinking about it as one or the other. I think these types of dualities where we think about things two different ways really aren't very foreign to Clojure programmers, right? Like when we're writing macros, sometimes we're thinking about the forms that we're processing as code, and sometimes we're thinking about it as data, and that comes pretty naturally to us. And similarly, when we're working with higher order functions, we're treating the functions we receive just like they're kind of opaque values. Sometimes we're treating functions as behavior. and again, that's totally normal and natural to us. And similarly, Clojure's data types are very interesting in that like maps can function as functions, right? We can call maps on keys to get values. Keywords can do the same thing. We can call keywords on maps to get values. So, these things are sometimes kind of functioning more like data, sometimes functioning more like functions. And those implementations in Clojure are quite clever because they really are pretty analogous to mathematics, or where functions are really mappings from their domain to their codomain, right? It's a natural representation, and it's great that Clojure borrowed that idea. But these dualities, it's not really an exotic concept, right? Sometimes my coffee table is a footstool, and that's how I'm thinking about it. Sometimes it's just a coffee table. It's not that weird, even though it sounds weird to say they have this dual nature. And my point here is really utilitarian. It's when we're looking at something, we should be thinking, what model is useful to understanding this? I'm not so much worried here about what is the ultimate underlying nature of the thing, what is its true form. Put that aside. This is not a philosophical discussion so much as a pedantic one, right? Can we shift our model in a way that helps us to understand what we're looking at right now? And I think that that's really important with transducers because we've talked about one view of transducers, which is as these composable algorithmic transformations. They're perhaps somewhat opaque functions, but we know that we can store them. We know we can pass them around. We can let them. We can use them with reduce and transduce. And we have some notion of what they do. But there's this other way of looking at them that I think you really have to understand when you start to get into implementing transducers and seeing how they work. And that is that you need to know that they are functions from reducer functions to reducer functions. And this was the key fact that really unlocked understanding transducers for me, and why I named this talk after it, and why I think this duality concept, even if it seems a little overblown, is worth remembering, right? There are these two different views, and sometimes one is better than the other for understanding the current situation. So what does it mean that they are functions from reducing functions to reducing functions? Well, we need to make a brief pit stop, and I need to explain that transducers reducing functions are just a touch different from the normal reducing functions we're used to thinking of with reduce. And I like to call these extended reducing functions, but they're like reducing functions, that take, let's say, an accumulator and an X or whatever and an input, you can call it what you like, but they take that concept, but they also extend it with two additional arities that have special purposes. Okay, so the two arity is what we just discussed. It's kind of this one step in the transformation. It's potentially add this value into this collection like conj does, right? But the other arities have these particular purposes that you mostly care about when you start to implement your own transducers. So the zero arity form is used for initialization. So we call the zero arity form on our nested transform. And the one arity form is used for completion. So if we have some finalization that we need to do after we've produced our new collection, then that's where this is used. Often these are no ops, but it exists so that it is possible for transducers to do something to produce a final value or to flush state. These things are really just part of the contract of transducers, and often you will provide pretty much no op versions of these functions, but occasionally you may need them and they're pretty handy. But just know that they need to be there for a reducing function to work with transducers. So let's implement a basic transducer. We're going to just make a very purpose-specific transducer that's going to increment each value that it sees. So we're naming this inc xf is a name you'll sometimes see, kind of stands for transformer. And we discussed that a transducer is a function from a reducing function to a reducing function. So don't be surprised that it takes a reducing function as an argument, and that what it returns is a function with three different arities as we discussed. Okay, so the zero arity form just calls the reducing function that it was given. Recall that this is kind of an initialization step. We have no initialization of our own to do, so we just fulfill the contract and we call the reducing function we were handed. Then the one argument version, this is the finalization. Again, we don't really have anything special to do, but when we are called, we will call into the reducing function that we have wrapped. And here's where the real work happens, right? Again, like any reducing function, we get an accumulator, we get an x. We are going to call the reducing function we wrapped on the accumulator and transform the value and pass that along. So you see that we're calling this other reducing function in the same way that we would call any reducing function, which basically means that we're counting on that function to do the next step in the transformation, whatever it may be, right? We've done our job here, and then we're just saying, okay, do what comes next. We know that this thing is a transducer, right? So we know that we're able to call into passing this. And when we do so, we can call it to transform this. And I haven't shown the output here, but the output would be 2, 3, 4, just like we would kind of expect with the transducer that increments each value. And also, just like any other transducers, we know that we can compose this thing. So we will compose our incrementing with our filtering to odd numbers. So just using a Clojure core transducer. And we see that we did, in fact, increment all the numbers and then other way around, we filtered to the odd numbers and then we incremented those, right? And again, remember the order of this is backwards from what you may intuitively expect. So that works. Maybe we kind of understand why it worked, but there are probably still some details that are fuzzy. But understanding that, we can now say, okay, much like we used reduce to implement map earlier, we should be able to generalize what we did here with the transducer to implement map, right? So we know that now we're kind of up a level higher, right? And we need to pass a function that returns a transducer, right? Rather than just defining a transducer itself. So you'll see that we have this outer function that takes a function and it's going to return a transducer that maps that function. So we shouldn't be surprised to see that the inside of this, it follows the description that we understand of what a transducer is, right? A function that maps a reducing function to a reducing function. The code in here looks basically the same as what we saw before, right? We have the 0 arity version does the same thing, the 1 arity version does the same thing, and the 2 arity version is exactly the same, except instead of calling inc here, we've called whatever function we've passed in, right? So we can use this thing in a similar fashion as before. Previously, we were just directly putting our inc transducer here, but now we're going to call this map transducer on inc to return an incrementing transducer. So the net effect is that it's the same as what we had on the previous slide, but of course it's higher order, it's parameterized, right? And in the second line, you can see that now we can filter and we can map and we get the same output, but now we've written something more generalized than just an incrementing transducer. We've written a mapping transducer that is akin to the one in Clojure Core. In a similar vein, right now we can try to implement filter. So this looks very much like map. Instead of F, we're going to call it pred, as is tradition. And then these are exactly the same. But here we see that we're going to choose between, if this value passes our predicate, then we will call the reducing function with the accumulator and x. And if it does not, we will just return that accumulator. Looks very similar to our filter implementation we wrote earlier using reduce, just with the added complexity of now there's this RF that we're calling instead of just calling something like a conj. Why all of this RF stuff, right? Well, the transducer's job is to transform and then call whatever it is that comes next, right, to accumulate. Since we are not defining what the data structure is that comes out of this process, that's not up to us, and we don't want to be tied to a specific data type, then we can't just be conjing or doing some operation that is specific to the data type. That's why that needs to be parameterized. How is it parameterized? By a reducing function doing that process and that reducing function getting passed in, right? So maybe that thing ultimately is conj, but it's handed to us with this opaque name and we just call it, right? So we do our step and then we pass control over to the RF, okay? And so if we have this chain of these transducers that are each calling RF, how do we escape kind of this infinite regress, right? At the end of that chain, there's got to be something that is not just a transducer calling another RF, which is a transducer calling another RF. And the way that that chain is ended is that ultimately the RF at the very end is an RF that is kind of a traditional reducing function that is actually going to produce a sequence or put something onto a core async channel, or does something material, let's say, right? So the key point is it doesn't call out to yet another reducing function. There is a final reducing function at the end. And where does it come from? Well, that's the job of what is called the transducible process, which is basically the context in which this is all running. So I want to show you that this is all correct, and then we'll talk a little more about transducible processes. So if you look at this example, we know that map inc is going to return a transducer, right? And we know that a transducer is a function from a reducing function to a reducing function. So that means that we can call it on a reducing function, in this case conj, right? And we get back a reducing function. What does that reducing function do? Well, logically, it must increment each value and then call conj. But regardless of exactly what it does, we know that it is a reducing function. So we know that we should be able to call it on a collection and a value. And here's our output, right? So we see that, in fact, we took 0, we incremented it, we conjed it onto this vector, and we got out the one we would expect. So you can kind of see that all of the types are correct here. And you can imagine that, this could even be a composed sequence of transducers. But at the end of the day, the thing that we get needs a reducing function to kind of terminate that chain. And then that reducing function inherently can do a step of its job by being called with a collection and a value, just like any reducing function, that we would pass to a traditional reduce. So now we're ready to talk about transducible processes, which are the things that actually drive the reduction, right? They answer the question, what ultimately happens with these values? Where do the values go? How do they get into the vector or the set, right? Or onto the core async channel. Like we've shown that each step, we are taking a value, possibly transforming it, passing it on to the next reducing function, whether that be a transducer itself or the kind of terminal reducing function in the process. But who sets this up? Who iterates this? And kind of determines where the values actually go, right? So we know from our usage of the transduce function and the into function that those are some of the ways that we can use transducers. So they must have the answers to this question, right? And so those are what we call transducible processes. And it's worth knowing that you don't just have to use the built-in ones, you can write your own. If you have a new situation you want to apply things to, a new data structure, a new potentially even concurrency mechanism, right? You want to, I don't know, map these to a future, something different, right, from what's built in. It's extensible. You can do whatever you want with it, right? So let's look at how we would ourselves implement the transduce function if we wanted to. And so we know, and again, I'm just going to focus on this core arity. So let's implement the transduce function, right? So we know that it takes a transform. This is the same as what's sometimes called XF. It's a transducer, right? And it takes a reducing function and an initialization value and a collection. So it's just like the signature of reduce, but with a transducer, right? We saw this early on using the built-in transduce. So how would you implement it? Well, it's not really that hard. Actually what we do is we call our transducer on the reducing function, which reducing function, we know that we get out a reducing function, right? So now we have this reducing function that does the combination of what happens in the transducer and the final reducing step. And then we just call reduce with that, right? So we're calling into just regular old reduce. We're saying our process for a reduction at each step is this compound thing that encapsulates the transformations, and ultimately, whatever the reduction function is, and passing along our initial value and our collection. And then the only quirk here is that we need to call it again at the end, because we said that the one arity form of this function is used to finalize the process, right? So we can use this exactly like the built-in transduce function, right? So here we're doing a reduce over these numbers with an initial value of 0, and we're mapping inc over each of those values. This is very similar to the built-in Clojure.core implementation of transduce. Finally, the other place that we've seen transducers used is the into function. And we know that into in its three-arity form takes a collection to add the values to, a transducer to transform them along the way, and somewhere to get them from, right? And all we do here is we call transduce, passing along all the same arguments, but the reducing function in this case is conj. And here we can prove that this works exactly like you would expect. So this is all it takes to implement a transducible process, right? So you can probably imagine what this would look like if, say, you were using core async and you were reading from a channel and let's say, outputting values to a channel, right? We know that we're going to have to provide some sort of reducing function that is going to take that channel and a value. That could, for instance, kind of be our f here, right? And we can kind of bundle up our transformations with that reducing function, and the function we get out is something that's capable of doing all of those operations together. And that's kind of the process, right? And so that's really it. If you do want to do a little more reading on this topic, there are a couple things that I was not able to cover in detail in the time that I had. One of those is stateful transducers. So transducers actually can maintain state. They may need to do this for purposes like, let's say, deduplicating, or really anything else you can imagine, but they can hold on to some state along the way, and there are some special things to know when you're doing that. Transducers can also do early termination, right? So if we had shown, implementing a take transducer, for instance, you want to terminate that process early so that you're not continuing to process additional elements from the sequence or whatever the input is. You do that with reduced. This is the same as just the traditional reduce function. I find a lot of people aren't familiar with this, but reduced is a special function you can call inside of something like a reduce that returns a special value that tells reduce not to go through any more iterations. It's extremely efficient. It's good to know about. So if you want early termination in a reduce or in a transducer, you want to know about that. Here are a couple libraries that give examples of transducers that are well implemented and interesting and practical, and utilities, that really let us do fancier things with transducers, higher level transducers that do pretty neat stuff. Good places to study up and learn a little more. Briefly, I want to plug the Austin Clojure Meetup, which is where I first gave this talk. It really is an incredible group of Clojure engineers. I can't recommend it enough. So if you're in the Austin area, we'd love to have you join us. I'm hoping that we'll work on getting more of our talks online as they're given. So if we can make that happen, please look for those. But it really is one of the most talented groups of engineers I've ever had the pleasure of being around. So I highly recommend joining that group if you can. Lastly, this is my website down here. I write a lot about Clojure. It's one of my favorite things. So please check it out if you're interested in more.